Okay. Espinoza. Okay, so we are talking about, we're in chapter 1, the properties of gases. So this is all about gases, right? The first, where we're starting out, is this idea of states and the state of a gas. What comes across, Madison, what comes across when they say a state, really of anything, much less a gas? It's state? Yeah, kind of like the state of a person. You kind of start thinking about how they're feeling and all that kind of stuff, right? More like a psychological thing. But here it's all with energy. So anything that would influence its energy in any way, it's going to be needed to describe the state. Okay? And I think it's easier to answer the question state, how do you describe a state, everything about that gas and its energy and where it's at and all those sorts of things, especially if it affects the energy, is where it's at. But if it doesn't, it wouldn't matter. Is the equation of state. If you know what the equation of state is, something that interrelates all these little parameters you're naming off, and then it's a lot easier to determine the state because you just look at the equation and you write down everything. Like the perfect gas. We call it the ideal gas law. Kathleen, what was the ideal gas law? PV equals nRT. So if you, here's one. PV equals nRT. And that was for this, we should have guessed, we should have put it down here, right? Equation of state for a perfect gas. But now if you know that equation of a state for a perfect gas, you just need to know it's what and you know its state. What would you have to know? It's temperature, it's pressure, it's temperature, it's pressure, it's volume. Yeah, little n is number of moles. Now, do you need to know all four of those? Because little r you don't need to know because r is gas constant. Do you need to know all four of those? No, you just really need to know three. You just really need to know three of them. Not all four. All right? You only need to know three. What is a perfect gas? Actually, literally, what is a perfect gas? Give you a hint. And this really isn't even true either. This much of a hint? Yeah, but they don't collide. That's where this little demonstration really falls short. Molecules that don't collide. So how can they not collide? That means they can't have any what? Yeah, they can't have any attraction. They also couldn't have any what? Intermolecular forces, intra-atomic forces, interatomic forces. Can't have any. What else could they not have? Could they not have temperature? These things molecules that can't collide. Can they have a temperature? Yeah, moving is all you need for temperature, right? You crank up the temperature and these molecules that can't collide, they just start what? If you crank up the temperature? Moving faster, right? Whatever it is they're doing faster, whether it's spinning, vibrating, flying around, they start moving faster. And there's different ways to move, but that's the idea. What else could they not have? Now, they can have temperature.
We're just saying that they can't collide with each other, right? They bounce off the container.
See, it's far from ideal, right? If they can't collide with each other, how could they collide with the container? They can't. Well, if they can't collide with the container, they can't have a what? Well, volume is... They can't have a pressure is what I'm driving at. They can't have a pressure. But they have to have a pressure. PV equals nRT. Right? And it is a lie. And if they can't collide, that's really what it's driving at, is the volume. They can't have a volume. This ideal gas just has to be mathematical dots. That's all an ideal gas law is. There's mathematical dots in space that are moving around, because dots can't interact, they're just mathematical. But how they can exert a pressure doesn't make any sense. How they can have a mass doesn't make any sense either. We have a little n for moles. They have to have a mass. But, it's the ideal gas law. The reason why you do it is because, dang, PV equals nRT really gives you good answers. Just even though you're just treating this real gas as dots, it has no volume, they can't collide, you get really good answers just using PV equals nRT. It's really powerful, right? This thing is all Michelin. Now, I don't think they use PV equals nRT. There's better equations of state. But they could use PV equals nRT in designing all their tires, make sure they don't blow up and stuff. It's just good for ballpark figures. What would be another equation of state that maybe Michelin uses? You remember this? I don't know if we had it in general or not. It starts with a V. Van der Waals. Van der Waals equation of state was another one. Okay, and I think we might get to that. Okay. Pressure and mechanical equilibrium. Oh, I forgot to bring it. Well, I guess this is a good example of pressure at mechanical equilibrium, right? It's a physical device used to measure pressure. I don't know if you can see it. This is open to the atmosphere, this tube is. So that means atmospheric pressure is here, followed all the way around. Atmospheric pressure is being exerted all the way inside this glass tube, right, inside all that air. What is the silver stuff? Mercury, right? Okay, now you look at, see then the mercury's, so atmospheric pressure is on one side, mercury, 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 all the way down. But then you have a closed end on this end. What's the pressure over here? On top of this mercury, on this column? It would be atmospheric if I busted it and clipped it off. But I didn't. It's sealed. In fact, how I made this is, see all these little wires, snip, take them all off, and you have this glass tube. You have a little piece of tubing, the other glass tube, and just have the whole thing straight, right? The other end is sealed, one end's open, and just slowly keep pouring mercury in, right? So the whole tube is filled from bottom to top there, and then you just rotate it up. So why would this fall down? Why would this level of mercury not be up here? Why did it fall down a little bit? Mercury's heavy stuff. It's gonna, all right? Why doesn't it keep falling out all the way out? Well, it's balanced. Right? What's pushing back? What's pushing back to keep that mercury from just leveling out? Something has to be. That's the whole mechanical equilibrium idea. Another gas. What are the gases? All this. Oxygen. What is all this is mostly what gas? It's mostly nitrogen, right? Why is our sky blue? Any planet that has mostly nitrogen, blue sky. What color? You should look at those rover pictures. You spent billions of dollars on this. You might as well look them up online. What color is Mars sky? Is it blue? No. So that means Mars' atmosphere doesn't have a lot of what in it then? Nitrogen. Okay. I think it's kind of red. I think that's what methane, that's the color methane likes to scatter. Nitrogen is great at scattering blue. That's why our sky is blue. Because nitrogen is really, it matches the size of the blue wavelength. Okay. So that means what's above this column on this side is what? Starts with the V. You can remember when I made it, it was all filled with mercury. And then I tilted it up. This was all filled. It falls down until it reaches mechanical equilibrium, pushing against what Juan said, the atmospheric pressure. What's up here then? Is there any pressure at all? It's just what's the V word? There's no pressure. Vacuum. A vacuum. There's no air up there at all. Now, technically speaking, though, and we're going to get into this, there is a gas in there. Brownie points if you know what it is. What is the gas? It's not a true vacuum. What gas is it? What gas could survive out of nothing? Doesn't even make sense. How could there really can't be anything there? There was nothing, right? And then the mercury level falls down. Well, little gas escaped through all. No. What do all liquids have? A vapor pressure. All liquids have a vapor pressure. They all do. That means you have a jar with a liquid in there, right? Part of that pressure, you got to seal it up, otherwise it's just going to evaporate on you totally, right? So you seal it up. Part of the pressure in that container is the pressure due to water. Part of the, well, the only pressure in here is the pressure due to mercury. You have to look it up in some table. See what the temperature is? That's the vapor pressure of mercury. That's right here. But it's also kind of right here, and this is a narrow tube, so it kind of cancels out. So when you measure this height, so what is this? Rob, you said you use this. What's it good for?
Measuring pressure.
Pressure of what?
We used it for pressure exerted by a vacuum.
Yeah, but right now it's measuring pressure. What is it measuring the pressure of? Atmosphere, right? What? See how this side is pushed down a lot higher than this side is. This side has no pressure on it, right? Well, technically it had the vapor pressure of mercury, but it's kind of canceled out because it's also over here. So this side, it really has no pressure on it. This side has atmospheric pressure on it. So you can measure the atmospheric pressure. You go to listen to the weather, the barometer reading. What units do they use sometimes? Millimeters of mercury. Now this is centimeters of mercury, but you could convert it if you wanted to. What is it? This is like 97 and 24. 97 minus 24 is 73. Is that right? So that's 73 centimeters, 730 millimeters of mercury. Why isn't it 760? Isn't that, oh, 1 atmosphere is 760 millimeters? Remember that? We're going to do that a lot. 1 atmosphere is 760 millimeters of mercury. Why isn't it 760? If it's supposed to be measuring atmospheric pressure.
Is it at the sea level?
That's at sea level. We're not at sea level. Are we higher or lower? Higher, so there's less pressure. All right. Okay. Okay. Equation of states. We've talked about a bunch of that stuff. What's diathermal versus adiabatic? How would you want a coffee cup? Would you want your coffee cup to be diathermal or adiabatic? Adiabatic. Unless you like cold coffee, right? Because adiabatic doesn't let heat across. Diathermal does. Metal cup versus styrofoam. Yeah, the stuff that lasts 1 billion years in the landfill. Okay. Oh, more like 1 million. Okay. Gas laws. I don't, like, I think PV equals nRT, so P is inversely proportional to V. I think that's Boyle's law. They like to play with this. I had never thought of it as being much use. Right? Because you have PV equals nRT. Why care about the individual laws? But anyway, how do you say this mathematically? Pressure is inversely proportional to volume. Yeah. Pressure is directly proportional to what? Temperature. Yeah, to see what's on top. Or directly proportional to number of moles. Okay, that's just playing around with the language. Okay, what else do we have? I think what's so limiting about the ideal gas law? How does it limit you? Why is it only ballpark figures and not exact? Why would it be limiting? What's wrong? What's wrong with the ideal gas law? You know, be specific. Like what?
Well, like the whole volume and pressure thing,
Yeah. Do molecules have a volume?
according to the ideal gas law.
Reality? Do molecules have a volume? Most definitely, right? So it's limiting. There's things that just don't. Do molecules collide? Yeah. The biggest one is what Juan hit on. Do molecules interact with one another? Under the, how else could we get a liquid? Right? Right? What's gases sticking together making a liquid? That's called, starts with C, condensation. So would the ideal gas law work very well at temperatures where water is condensing? Or is it going to be way off? It's going to be way off because those molecules are interacting. That's the idea of a limiting law. Is in certain situations, man, this just isn't going to work. Okay. So when you, especially when you have molecules interacting, you shouldn't be using the ideal gas law. So that means really, what conditions should you use the ideal gas law? All right. You have PV equals nRT. What conditions should you really be safe using the ideal gas law? Does volume matter? Not really. I mean, they got to be somewhere. How about the number of moles? There's got to be something there. Otherwise, you have no problem. It's pressure and temperature. Under what pressure conditions would the ideal gas law work the best? I guess look at the extremes. Really high or really low? Really? Why really low? Because if it's a really low pressure, are they going to be colliding with one another? No. So it's acting more ideally. How about temperature? Now, really low temp, you're going to get this to happen. Right? They're going to start interacting. So the answer must be really, really high temp. Because otherwise you're going to have this. You want the opposite extreme. You don't want a condensation going on there. Okay. Avogadro's. Dalton's law. Dalton's law. Okay. Pop the lid. Does everybody agree I have atmospheric pressure in here right now? Right? Do I still have atmospheric pressure in there now? I mean, let's say I put the lid on nice and slowly. Right? Okay. I do, right? Still have atmospheric pressure. What is that atmospheric pressure? It's, what did we say, 73 centimeters? Okay. That pressure, that's 73 centimeters, can be represented in a mathematical equation right here. There it is. What is it? Partial pressures. Every single gas in there indicates, gives off its own little pressure. You add up all those little partial pressures, it shouldn't be a little p anymore. It should be big P. Right? That's a total pressure. Add up all those partial pressures. This is where it gets curious, I think. What are the gases that are in here? We already mentioned some of them. Nitrogen, oxygen, carbon dioxide, there's a little bit. Any others? Oh, definitely not. I can definitely say there's no hydrogen. Why? Because Earth, we're on Earth, can't hold what two gases? Hydrogen and helium. That's why the balloons, right? Gravity's way too weak. You got to be on Jupiter. Then you could say hydrogen, but not on Earth. So definitely not hydrogen. There's one other one. Water vapor. All right. So you list them all out. Right? You can actually start listing them all out. You got the nitrogen. My total pressure would be the nitrogen, the oxygen. I think Rob said the carbon dioxide, right? There, actually, argon is a good one. And then we said water vapor. Okay, so there's actual numbers for all these, right? Okay, let's say we find out what that pressure due to water is. It's some number, right? In here, it's some number. Okay. Did the vapor pressure, did this change? Did that change? I mean, there's still some water in there, but I dumped out a lot. Did it change or not?
Same number of molecules of water, like the same substance.
Yeah,
You had the original.
we're getting there. Density of water. Is that an, this is where terminology really helps. Is density an intensive or extensive property of water? You remember playing that game? Does it matter how much water you have? The density is the same. It doesn't matter, right? So density is a intensive. Density is an intensive property of water. Okay. Give you a hint here. Why? Fine, you big baby. I'll have to do it myself. Whoop. Ain't there. Where did I put it? You've seen this. Oh, that ain't it. Where is it? Where are... Everything moved on me. Courses. Oh, here it is. Shouldn't be allowed to move my icons around. You've seen stuff like this, right? You look up the temperature and you record the vapor pressure of water. It looks like vapor pressure of water is an intensive or extensive property. All right? You name me a temperature. It's like 30 degrees in here, right? I don't see a 30 on here. Maybe it's not that hot. 30 is kind of hot, right? It's more like 25. What's torr? See how it says torr? Unit of pressure. 1 torr is, does anybody know? 1 millimeter of mercury. It's the exact same thing. Okay. So you can pick any temperature you want, and we can record the vapor pressure of water. So is the vapor pressure of water an intensive or an extensive property? Is this ever going to change on you? The only way to change is to change what? According to that table, temperature. That is the only way to change vapor pressure. So it doesn't matter how much water I have in your liquid water. As long as I have a drop, I have that vapor pressure of water. Now, why is that a big deal? What is boiling? Why would I put this on the heater, my container of water here, and I get the darn thing to boil. And I heat it up, heat it up, heat it up, heat it up, heat it up. Why does it start boiling? Why? What is happening to this vapor pressure as the temperature goes up? It's going up. What happens when that vapor pressure reaches, what did we say the pressure was? 730 centimeters. What happens when that vapor pressure, and it's going to hit it sooner or later, what happens when that vapor pressure hits 730 millimeters, or 73 centimeters, or 730 torr? What happens? Boil. There's not enough pressure to keep that, keep it as a liquid. It's all of it. That whole kettle is now a vapor. And you see those little bubbles boiling from everywhere in here. The whole thing is trying to turn into a vapor. There's just not enough energy for all of it to do it. But if there was, it would just go poof. Okay? And some liquids can do that. In fact, one of my organic chemistry was in there, and you had to heat up some ethanol. And so I got the little ethanol container, poured it in. They must have had new beakers, and I mean, I don't know. Everything was super clean. I guess maybe I was really anal or something. I don't know. But everything was super clean. So I get my ethanol, I put it in, and I had to heat it up to whatever temperature for this stinking organic lab, right? So I heat it up. I put it on every time I heat it up. Well, I fill it up the container first. I put it on the burner. Poof! It just blows up in your face. Oh, jeez. So I do it again. Pour in a little bit. Do it much more slowly. Poof! Right? Until I finally figured out what's going on. What's going on? It's just this was so hot. This was so clean. Like I said, when something's boiling, the whole container wants to turn into a vapor. That's right. But they need something. Those bubbles need something to grab onto to form a bubble. You need some crap in there. You need some little hygroscopic nuclei is the technical word. You need something for those bubbles to start forming on. You need some dirt. If you don't have any dirt, or what do you guys use? You guys don't use dirt. You use what chips? Boiling chips. I'm in a rush, man. Organic. Who the hell needs boiling chips? They're just going to boil anyway. So who needs boiling chips? You need them. Otherwise, if you have a really clean container, poof, the whole thing's going to not blow up. It just turns into a vapor in your face. And if it's flammable like ethanol is, it's probably not a good idea. But since it was an electric burner, not a flame one, I guess that was okay. All right. So that's why you use boiling chips. Let's see. So I think that's about all I have to really say. Oh, just to play around with these equations a little bit. What's this PJ? What's this PJ? Let's pick one. PJ equals NJ RT over V. What's that? No. PJ is just, they're trying to be consistent with their notation. J is just a counter. So J could be A, B, C, or D, or whatever. But if you have PA, then you have NA. So PA would be the pressure, well, the technical word would be the vapor pressure, or the partial pressure of gas A. NA would be the number of moles of gas A, right? So that's all it is. If you pick the partial pressure of nitrogen, well, then you just have to plug in the number of moles of nitrogen. And there's one other equation up here. I don't know if you remember it. But if I divide both sides by nRT, I get PV over nRT equals 1. And what I can do is just put little initials or ones on these. All right? And I could do the same for final conditions, P2. All right, so I'd have P2 V2 over N2 R T2 equals 1. So I can set these guys equal to each other, right, and solve some problems. But notice the equation is really simpler than that. P2 V2 over N2 R T2. What can you cancel right off the bat? You're not going to see this equation. What's going to cancel on you? What'd you say, Juan? The R's, right? They're gone. You're never going to see those. And if the amount of gas doesn't change, which it hardly ever does, what's the new pressure? They give you these initial conditions. What's the new pressure? Little what's going to cancel? Little n. That's almost always gone on you. But I'm not, just to cover all cases, we can leave it in there. But okay. So let's take a look at some of these. So we've got some equations to mess with. Now, when you start taking quizzes and exams, you go to the very end of this. This is what I'm giving you. We're going to take an exam after every chapter. I'm going to give you all this. If it's not here, oh man, I better know it. It must have been something we derived, or like this whole P1 V1 over T1 equals P2 V2 over T2. Is it there? It's not even there, right? So it's something that you need. Is it there? Where? It's not. There's some new equations of state down there, but no. So that's just something that you need to realize, that PV equals nRT, so I can set up that relationship. Okay, so let's take a look at some of these. Exercises 1.1. So any questions on what's going to be expected? If I give you a quiz, I'll have that equation sheet for you to use. Oh, we kind of skipped something. If we're going to use PV equals nRT, or if we're going to use, or if we're going to use this thing, this equation, where'd it go? P2. Or if we're going to use that, what does T have to be in? Kelvin. Has to be in Kelvin, right? In fact, all you do is just match whatever units R is in. R is what really determines the units of everything. Okay? Because sometimes R is in liters, sometimes it depends on which R you pick. A sample of air occupies 1 liter, 25 degrees Celsius, and 1 atmosphere. What pressure is needed to compress it to 100 cubic centimeters at this temperature? Well, probably use what? What's the clue that you're going to have to use that P1V1 equation? Yeah, I think too. That's a hint to me too. Oh, what's a final volume? That means they're changing volume. There's more than one volume, right? In that equation, we can cancel anything? Temperature, definitely, right? At this temperature. That's why they didn't give it to us. Oh, they did give it to us, didn't they? But you didn't need it. So you can convert it into Kelvin and substitute it in. It's not going to hurt anything, but it's just kind of like extra work. Okay. Now, if we plug in P1 in atmospheres, P2 is going to come out in atmospheres, right? You plug V1 in liters, that means V2 had better be in liters. Okay, so there's a problem right there, I guess. But we had a concept preview. What do we know? A cubic centimeter is? 1 milliliter. 1 cubic centimeter was 1 milliliter. That's how it was defined. It's just a unit of volume. They're the same thing. So if you have 100 cubic centimeters, you'd have 100 milliliters. Okay. So this is something that I'm interested in seeing what you want to do. Do you want to finish this problem and work on to the next one, or do you want to just try to set up as many of these as we can? What do you want to do? This is your homework, and you're the one who has to figure this out at home. Just keep going. So does everyone set up? Okay. It'd be more fun for me, but you're the one who has to get through the class. Right? Otherwise, I'm just sitting here. Okay, Rob, are you done yet? So everyone's comfortable with this? All right. Let's check out the next one then. A perfect gas undergoes isothermal compression. Now, they're getting some terminology here. What's isothermal? Temperature stays the same. Okay. Which reduces its volume by 2.2 liters. Okay. Is this using the same type of equation we just did, you think? Right? It's the only relationship we have for changing conditions from one pressure or one volume to another. You pretty much have to. Yeah, it's always going to be perfect gas. Yeah, we don't need it. They like to start out the same all the time. So we're going to have P1 V1 equals P2 V2. Calculate the original pressure of the gas. So I picked P1 too. They want us to find this one. That means in that problem, they had to have given you the other three. They had to. I think they're all in there, right? Okay. How about going from torrs to atmospheres? How are you going to do that once you finally get your P1? Yeah, I think it's 760. Because there's 760 millimeters. If you look at the inside front cover are all the conversion factors. But 1 millimeter of mercury is 1 torr. Oh, they have it. So 1 ATM 760 torr. Okay. Not so bad. Okay. How about 14A? Oh, 1.4A, sorry. Yeah. You see two volumes. We only have one relationship when you have two volumes in it. That's kind of a hint. Is it this guy again? Yeah. What are we going to say about pressure? To what temperature must a 1 liter sample of perfect gas? So we know the... Yeah, they have to. That's where some of these questions get tough, because you have to make some assumptions. I think I would agree with that. You're going to have to assume the pressure remains constant. What's the word for that? They should have said isobaric. 1.6. So you're okay with 1.4? How about 1.6? Oh man, you guys are getting let off so easy on a 3-day weekend. Yeah. Yeah, don't get used to this. Okay. So just plug and chug on that one, right? How do you get milligrams into grams? Move the decimal place how many times? 3, or divide by 1,000. And you got to get it converted into moles. Neon is what chemical formula? Ne. Yeah. I think you got it. It'd be hard to screw up on that one. How about... Oh, okay, now we're getting into something good. We got to do a little thinking on this one. Okay. At 500 degrees Celsius, I better start writing stuff down here. And 699 torr. See, I like listing things out like this because if you need to do any converting, you just convert it up there before you substitute in. It's kind of cleaner. The mass density of sulfur vapor is 3.71 grams per liter. What is the molecular formula of sulfur under these conditions? Molecular formula of sulfur. So is there any other element besides sulfur present? Is there anything else besides S present? Yeah, other S's, but that's it, right? Just S's. So isn't your answer going to look something like this and then some number down there, right? This is what we're after. That is what we want to find. Question is, how are you going to get it? Any ideas? If, let's say, let me give you a little hint here. Let's say you had, what would be an example? O2. What's the molar mass of O2? 32, right? And how'd you get it? You multiplied 2 times 16, okay? N2, and well, maybe there's such a gas. N3, I doubt it, but what would be its molar mass if it existed as a gas? 3 times that. So my point, what I'm trying to get at is, if you know the molar mass, all you do is divide it, right, by the atomic mass, and you'll get the number of them, and you write the little guy down there as a subscript. That's all we got to do. We need to find the molar mass. MWT. Okay, now I didn't hear what you guys were saying. Find MWT. I just wanted to get that down. That's what we got to do. So what were you saying? Well, we can't because we don't know what the molar mass is. Okay, I hear something about an N. I don't know. Maybe it'll help. Let me give you another little guide here. What is molecular weight? What are the units for it? What is it? Grams. Now, we like to say grams per mole, but it's so limiting. What I'm trying to get you to think of, is that it's the number of grams all over the number of moles. It's an equation. If you know the number of moles and the number of grams, you divide the two and you get molecular weight. It's an equation is all it is. The units kind of tell you what it's grams per mole. Yeah, you're right, but this is kind of easier. And what I'm driving at is we kind of know the number of grams. What's the easiest one to pick? Assume the volume is what? You know the number of grams. Assume the volume is 3.71. Or sorry, not 3. Assume the volume is 1 liter. Then the mass is 3.71. That's the trick to doing this. That is 3.71 grams if V is 1 liter. Now I bet you know what to do. Right? What would you do next? What's that? Yeah. There you go. Find the number of moles. There you go. You'll have it. Find little n. And put that little n down for the number of moles. Find the molecular weight, divide it by the atomic mass of sulfur, which is, I can't even see it, 32 or something. And you'll get, I don't know, 4, 5, 6, 7, 8, I don't know, whatever, something. And that's what you put down there. Okay, are you comfortable with 1.8? What's that? I think it does. It looks like something similar, doesn't it? Because they tell us the density. I think you're right. Just assume what volume? 1 liter. Then you know the number of grams. Use PV equals nRT to get N again. You're right. It's just like the first one. The one above it, I mean. And I think that's it for the homework. Oh, no, we have a problem. Okay. So we're okay with this? I don't know if we have time to get through this. Let's see. Probably, yeah, you have some stuff to do here. Okay. Okay. You need the book. There's a hint to solving this question. We don't have. Well, we might have. We should get you started on it. Page 16 in the book. I scribbled down in my notes here. Page 16 in the reading. The pressure at the base of a column is rho GH. And we kind of had that in the concept preview. But if you're down so far, right, that pressure, I guess you could say, at some depth, at depth H, you have the rho GH, right? Because it's the weight of everything above you. But what's above the water? Air, the atmospheric pressure. So whatever plus, right, I almost have to draw a diagram. Whatever you call this pressure, whatever you call that, atmospheric or P1, and then you're down here, there's supposed to be a diving bell. How do you draw a diving bell? Ooh, right, and there's some little guy in there. Right? I don't know. But see, you got the water pressure pushing up on you, and you have what's the total pressure inside there? Right? Well, then you have this rho GH too. And what was rho again? Density. Right? G is gravity, H is height. You need to make sure all these units, the easiest thing to do is to have pressure in standard metric units. Because then you know what, right? If this is in standard metric units, pascals, then, for example, gravity in standard metric units is meters per second squared. Height needs to be in meters. And this density, standard metric units for density would have to be in, usually it's grams per mil. Kilograms per, not liter, standard metric unit for volume. Not liters. Length times width times height, but in standard metric units, cubic meters. It's weird, but that's how it's got to be. I check out the, I think the concept preview might have played with that a little bit.
Would we put negative 50 meters? Is there
Oh, just the height. I wouldn't put negative because then you're going to end up reducing your pressure. You want to be adding, pressure needs to add up and combine.
It's all like physics.
Yeah, no. We're just adding up pressure, so it's absolute values. Yeah, technically with our little diagram, we should put a little P1 there. Okay. We're about out of time. But if you have something to do for the next 3 days, that's good. All right?